അതിന്റെ സൗണ്ട് ഇപ്പൊ കാണാം. അതെ ഷഫീഖ, ഈ രണ്ട് റോയിലായിട്ട് ഒന്നിച്ചേ പോകുള്ളൂ? ഇല്ല ഇല്ല, ലൈറ്റ് എന്താന്നില്ല. ഓക്കെ സാറേ. Hi, good morning, everybody. So good morning. Let us start. Today's discussion is on, as what we see on the board, to linear algebra. And many of the geometrical facts, algebraic facts about matrices, all you know. And if you study these items with a geometrical perspective, what you get, that is linear. So we can say linear algebra is a study of the theory of matrices, the theory of linear equations, the theory of determinants, etc. So we will be always having this geometrical flavor in this discussion. So let us go to the details now. Let us start. I'll ask you a very simple question. First, you consider the matrix A, which is a 2 by 2 matrix with all elements 1. The question is, how many matrices B exist with the relation AB equal to A equal to B? And you have choices. None. In only one, finitely many, infinitely many. So you have a given matrix A with all 2 by 2 matrix A, and you are asked to find how many different matrices B exist. Satisfying AB equal to A equal to B. You know the rules of matrix multiplication. And if two matrices are to be multiplied, like you take one matrix as the first one, the other as the second one, what should be the kind of orders of these two matrices? So here, the matrix B is multiplied. Go ahead. Ah, the matrix B is multiplied to the matrix A, first on the right and then on the left. And because A is a 2 by 2 matrix, the only possibility will be A has sorry, B has order 2 by 2. So that you know. And one more thing you know from the law that identity matrix always will be the candidate for B. So if you feel that the question is, do you have matrices other than identity matrix also? Do you have matrices other than identity matrix also? So is identity matrix that is a question. You will just look into some of the theory of linear equations. We will assume A to be a matrix, 2 by 2 matrix, with different entries A, B, C, D. And if you try to write the equation A B equal to A, that will imply 1 1 1 1 times the matrix A B C D equal to the matrix 1 1 1 1. That will lead to the equations A plus C equal to 1 and B plus D equal to 1. Similarly, if you write the equation A equal to BA, that means the matrix B you are multiplying on the left side of A, again you will get two similar equations. They are A plus B equal to 1 and C plus D equal to 1. So altogether you have two sets of equations. A plus C equal to 1, B plus D equal to 1, A plus B equal to 1, C plus D equal to 1. These four equations. Now, keeping A to be an B you can write using this relation as 1 minus A. And using this relation, you can write C equal to 1 minus A. And the only choice for D will be D equal to A. So you have the matrix B in the form A, 1 minus A, 1 minus A, A. When you look at the entries of this matrix, it's very clear that B is a symmetric matrix. And do you find any other property for this matrix B? You can easily check the sum of row elements. What is sum of row elements of the first row? A and 1 minus A. The sum is equal to 1. And that of second row, 1 minus A and A. And the equal to 1 for first column, second column. So B is a particular type of matrix. It should be a symmetric matrix. And it should have the row sum and column sum to be 1 on all rows and all columns. So such a matrix B will be the answer to all questions. And what is the entry A? A can so if you take A to be 1 by 2, you will get a particular matrix B 1 by 2, 1 by 2. So if you take A to be something else, if you take A to be 1, you are getting B to be if you take A to be 100, you will get corresponding values in the other and you will get the matrix B. Now, the answer to the question will be there are infinitely many B satisfying the relation or the condition AB equal to A equal to BA. Now, let us move one step further. If you have a 3 by 3 matrix of the same type, what will be the situation? If you have a 3 by 3 matrix, A equal to 1 1 1 1 1 1 1 1 how many matrices B you have satisfying the equation AB equal to A equal to B. With your previous experience, you can find infinitely many matrices. That should be the correct case. And then matrices B should be symmetric matrices. And what should be the speciality of the entries of the symmetric matrix be? The row sum and column sum all must be 1. The row sum and column sum all should be 1. So the matrix B can be taken as any symmetric matrix. The sum of elements of any row or any column to be 1. And three numbers having a sum equal to 1 can be found in infinity many ways. So, answer to that question will be in infinitely many. Now, with this question, you might have understood how we will attack one program in a different way. Now, we should have a geometrical idea what matrices are. So, what is matrix? A geometrical idea you should have. And what is system of linear equations? For that also we should have a geometrical idea. Actually, what is a system of linear equations? They are equations of the form ax a1 ax plus by a1 x plus b1 y equal to c1 a2 x plus b2 y equal to c2. So this is a pair of linear equations in two variables, and this can be written in the matrix form ax is equal to b, where a is the matrix a1 b1 a2 b2, and b is the matrix sorry x is the matrix xy, and b is the matrix c1 c2. If three linear equations are taken, if three linear equations are taken, the corresponding form will be Ax equal to B, where A is the matrix A1, B1, C1, A2, B2, C2, A3, B3, C3, and X is the matrix X, Y, Z, B is the matrix D1, D2, D3. So this is the way you write. And in this again, let us see, this is a 3 by 3 matrix. And this X, Y, Z is a column matrix. And D1, D2, D3, that is again a column matrix. Let us relate the matrices with the points in the three-dimensional space. You can easily say the column matrix XYZ represents the point XYZ, the point XYZ on the real space in the three-dimensional space. So, if you have the coordinates XYZ, these three coordinates will represent a column matrix X, Y, Z. So in that sense, the point as well as this matrix are same. Usually we have the habit of writing AX. So the column matrix X, you are multiplying on the right side of the matrix A. Suppose you write XA, the order of the matrix should be, there should be one row and three columns. Sorry, one row and three columns. So it should be of this form X, Y, Z. So this is a way we row matrix is taken. But usually X is not a comfortable style of writing. So I'll be always following AX. So X always you take as a column matrix. And if, because it's representing a point, and because you have the concept of position vectors to represent points, you can even call this column matrix to be a column vector. So we call x equal to xyz to be a column vector. So in this matrix equation, Ax is equal to B, A1, B1, C1, A2, B2, C2, A3, B3, C3. That is a coefficient matrix or matrix of coefficients. Capital X equal to the column matrix XYZ is the matrix of variables, and capital B equal to D1, D2, D3, that's column matrix, is the matrix of constants. Okay. Now, actually, this matrix product AX is equal to B, the matrix product AX is equal to B is telling what? The point represented by the column matrix XYZ is converted into another column matrix D1, D2, D3. Or you can say a matrix is changing points. Here the matrix is 3 by 3 matrix. A matrix 3 by 3 matrix is changing or mapping points in the three-dimensional space to points in the three-dimensional space. So, if something is changing points of a set to points of same set of another set, you call that to be a function. So, for us, matrix is a function. And we will study or look into what are the properties of this function. What are the properties of this function? So in that process, we will have many geometrical ideas also. And the equations Ax is equal to B, if in that the matrix B equal to 0, we will say the system is a homogeneous system. And if B is a non-zero matrix, non-zero column matrix, you say Ax is equal to B is a non-homogeneous system. And what do these represent geometrically? Again, that's another question. A linear equation of this form, Ax plus By equal to C, is a straight line in the two-dimensional plane. So you can draw it as a straight line. A linear equation of the form Ax plus By equal to C is a straight line. And if you have A1x plus B1y equal to C1, A2x plus B2y equal to C2, they are two straight lines drawn on the expand plane or on the graph paper. Okay, so when you draw two straight lines on a plane, there are three possibilities. Either the two straight lines will intersect, or the two straight lines make one side, or the two straight lines will be parallel and they won't have any points. So these three cases we have studied in the kind of they are in the system of linear equations separately. Still, these are geometrical implications. If a1x plus b1y equal to c1 and a2x plus b2y equal to c2 are two linear equations, then they will represent 2 points. And in the case of homogeneous system, because b equal to 0, the two straight lines should pass through the origin. Why? Because in the case of homogeneous system, C1 and C2 will be 0. So what will be the equations looking like? A1x plus B1y equal to 0. A1, A1x plus B1y equal to 0. A2x plus B2y equal to 0. And in this linear equation, because you don't have a term, that should represent a line passing through the origin. So if you draw the graph, and if two straight lines are drawn, both are passing through the origin. Origin will be a common point. So if the two straight lines intersect, then you will get origin is the only common point, and so origin is the only solution. And if you draw these two straight lines, which are in such a way that they will intersect, we will say, in other words, geometrically, the two straight lines have different slopes. The two straight lines have different slopes. And how will you write the two straight lines have different slopes? See, what is slope of this equation? A1x plus b1y equal to 0. That is minus b1 by a. See, is it not? The slope of this line will be, slope will be minus b1 by a1. And slope of this line will be minus b2 by a2. So if the two lines are of this type, what is the meaning of it? The two straight lines are intersecting means they have different slopes. So minus b1 by a1 and minus b2 by a2 are different. Minus b1 by a1 and minus b2 by a2 are different is otherwise told as a1 by b1 and a2 by b2 are not equal. A1 by b1 and a2 by b2 are not equal. And that is otherwise written as a1 b2 minus a2 b1 is not equal to 0. And what is a1 b2 minus a2 b1? What is this quantity? This quantity is the determinant of the coefficient matrix. So for a homogeneous system, in order to have in order to have a unique solution or only zero solution, the condition is determinant a1 b1 a2 b2 not equal to 0. So this will give you the condition for the pair of straight lines to be having a unique solution. Now, if the two straight lines are coinciding, if the two straight lines are coinciding, how will you get it? How will you get it? Oh, you will get first straight line is drawn through the origin. Second straight line, you again over that. So in that case, the two straight lines are coinciding. Origin is always a common point because you have the equation of the form ax plus by equal to 0 because it doesn't have a constant term, here the constant term, it should pass through the origin. And because they have equal slopes, all the points will be common. All the points will be common. So in that case, what you can say about the determinant of the coefficients, or that will be 0. So you get the slopes are equal. So a1 by b1 equal to a2 by b2, or equivalently a1 b2 minus a2 b1 is equal to 0, or determinant a equal to 0. So if in the case of two equations with two variables, that means you are working on the if two linear equations are considered, when you write the matrix form Ax is equal to B, when you write it in the form Ax is equal to B, A is a 2 by 2 matrix, X is a column matrix of order 2 by 1, B is another column matrix of order 2 by 1. And in that case, if determinant A not equal to 0, you have only the zero solution, x equals 0, y equals 0, intersect only at the origin. And if determinant is not equal to 0, the two straight lines are coinciding, or you will have infinity solutions. So the essence is a homogeneous system is always possessing a solution. A homogeneous system always possesses a solution. Now, in the case of non-homogeneous system, things are different. You can have two straight lines drawn on a plane if you consider two equations with two variables. You can have two straight lines, and the two straight lines can intersect at one point. That point earlier in the system, the point of intersection was at the origin. But in the case of the point of intersection can be some other point also. And this is one case. And another case is the two straight lines are parallel. I'll draw a smaller graph for it. The two straight lines are parallel, extended to both sides infinity. And another case is the two straight lines are coinciding, one over the other. So how these can be written using conditions as we did earlier. So in the case of a non-homogeneous system, the problem reduces to finding the point of intersection of two straight lines, which may be a point other than the origin also. Clearly, there will be exactly one point of intersection if the two straight lines have different slopes. So let us check these with some examples. So try these yourself now itself. I'll give you a little bit of time. X minus 2y equal to minus 1 and x plus 3y equal to 3. These are the two equations. You know how to write or draw the graphs, etc. So you prepare simple table, put the value x equal to corresponding for the first line as well as for the second line. You draw the graph. So I have already drawn the graph, and from the graph it follows that the point of intersection is this one. So it is 3, 2 almost. From the graph, it looks like the point of intersection to be 3, 2. So x equal to 3 and y equal to 2 is the solution. Again, look at the equation and coefficients. Coefficient matrix is 1 minus 2 minus 1 3. And that is a non-zero determinant. That has got a non-zero determinant. And because the determinant is not equal to 0, you say the matrix is non-singular. The non-singular matrices are having inverse. So if you write a matrix equation Ax equal to B, if A has not inverse, what is x? X equal to A inverse B. So B is given to you, B is a known matrix. A is given to you, its inverse is unique. So A inverse will be a unique matrix. A inverse times B will be a unique matrix. Or X will be a unique matrix. Or there is a unique solution. So if determinant A not equal to 0, we will get a unique solution. And in the case of 2 by 2 matrix with this equations, x minus 2y equal to minus 1 minus x plus 2y equal to 1. Consider these equations. Again, you consider what is determinant A. Determinant A, because you are taking 1 minus 2 minus 1 2, 1 minus 2 minus 1 2 is the matrix. Determinant will be 0. And determinant is 0. You got the two lines coinciding. And so what additional property you have? You find out what is adjoint of the matrix. Adjoint of the matrix is 2 2 1 1. You know what is adjoint of a 2 by 2 matrix? If A equal to A, B, C, D, adjoint A equal to what is the cofactor of A, it is D. And what is cofactor of B? It is minus B and minus C and A. So you get adjoint. In that way, you find the adjoint of this matrix A, you get 2, 2, 1, 1. And now you find what is adjoint A into B. You find out adjoint A times B. What is this? That also you calculate. You calculate that and you find that to be 0. So in the case of the two straight lines given by the equations x minus 2y equal to minus 1 and minus x plus 2y equal to 1, you get the two straight lines to be parallel, and for that the matrix satisfies the conditions determinant A equal to 0 and adjoint A into B, that also is 0 because this is a 0 matrix, 0 column vector. So it can happen that so what you get in that case you get, so if adjoint A into B equal to 0, determinant A equal to 0, these two together will imply infinitely many solutions. So for a non-homogeneous system of linear equations, if determinant of the coefficient matrix is 0 and adjoint A into B equal to 0, these two they together will give you infinitely many solutions, and as far as the consistency of the system is concerned, the system will be consistent. What is the meaning of the system is consistent? Consistent means the consistent means there is solution. So a linear system, non-homogeneous linear equation system will be consistent if either the coefficient matrix is non-singular. In that case, there will be exactly one solution. And if adjoint A into B equal to 0, there will be infinitely many solutions because the two, in the case of 2 by 2 matrices, or in the case of two equations with two variables, they draw lines on a plane, so they will be coincident lines. Now, it can happen that the non-homogeneous system to have no solutions at all. That you consider the system x minus 2y equal to minus 1 and minus x plus 2y equal to 3. As before you draw the graph of these two equations, you will get the two graphs to be parallel lines. Parallel lines means what? They will be so they cannot have a long point. And now, in this case, we check what are the conditions satisfied by the coefficient matrix and the constant matrix. Okay. So here, determinant A equal to 0. That is, the determinant of the coefficient matrix is 0. And the adjoint A into B, that you can calculate to be 0, 2. So it's a non-zero matrix. So if adjoint A into B is non-zero, adjoint A into B is non-zero, if determinant A equal to 0 and adjoint A into B not equal to 0 matrix, that means the non-homogeneous system is inconsistent. The non-homogeneous system is inconsistent if these two conditions are satisfied. Now, let us go to the three-dimensional case. An equation of this form, ax plus by plus cz plus d equal to 0, you call in the three variables x, y, and z. And geometrically, this represents a plane in the three-dimensional space. In the three-dimensional real space, this is representing a plane. So, if three such equations are given, what will be the geometrical implication of it? So, you can imagine there is there is a floor and two walls meeting at one corner of the room. So, there are three planes. And the three planes are meeting at exactly one point. That means you have one point common to all three planes. So if you draw or if you write equations corresponding to these three planes, that means the equation of the floor, equation of one wall, equation of the other wall, then you get three linear equations. They form a system, and that system has got a unique solution. Suppose you imagine three planes in such a way that they are the pages of your notebook. The pages of your notebook all will be bound along one straight line, which is the line containing the binding of the pages. So three different pages you take, so just take it beginning of the book, and in that case I'll show you a book. So I'll show you two pages, two planes are there. So if you take one more page in between, you will get three planes. And these three planes are having a common line, a line of intersection of the three planes. And in that case, there are infinitely many points common to all the three planes. Is it not? So that situation will be giving you, as in the earlier case, determinant A equal to 0, epsilon A into B equal to 0 will give you infinitely solutions. And in the case of three equations with three variables, you are getting the three planes having a common line of intersection. Okay. And you can have the condition determinant A equal to 0 and epsilon A into B not equal to 0 is satisfied. In that case, you can have the three planes having no common points. So you can imagine that also. You will be sitting in a room. The floor is one page, one plane. The two walls on either of your sides, left side and right side, that you can imagine. So they are three planes in three-dimensional space. But there is no point all the three planes. So that geometrical situation you can write as the condition ax plus determinant a equal to 0 and epsilon a into b not equal to 0. So let us have a simple case. Let's have a simple case. If you consider these three equations x minus 2y plus z equal to 0 minus 2y minus 8z equal to 8 minus 4x plus 5y plus 9z equal to minus 9. These are three planes and they will be having, say, hope you can see it, they will be having one common point, and that common point is 15 and 3 coordinates. So you can say x equal to 29, y equal to 16, z equal to 3 will satisfy all the three equations. And it is easy to check that in that case, the determinant of the coefficient matrix is non-zero. And because the determinant is non-zero, as per the theory of linear equations, you have exactly one solution given by x equal to X equal to A inverse B. X equal to A inverse B. That will be the solution. Okay. Now, the systems of linear equations is thus geometrically explained. Now, you come to the real geometry when math. So, and one more thing I'll say. See if A equal to Aij, I equal to 1 to etc. M, J equal to 1 etc. It's an M by N matrix. And B, Bjk, J equal to 1 to etc. N, K equal to 1 to etc. P is an N by P matrix. Then the product AB is written as CIK, where the general entry CIK is summation J equal to 1 to N Aij Bjk. So I'll tell it in a different way. Suppose you have the two matrices in this format. Okay. So A is having the different row elements and B is having the different row elements, column elements. When you take the product A into B, A multiplied with B, A on the left side, B on the right side, the number of elements in this row should be equal to number of elements in this column. Then only you can have the multiplication what A1 into B1 plus A2 AI1 into B1J plus AI2 into B2J plus etc. plus AIN into BNJ meaningfully. If you want to find that sum meaningfully defined, the number of elements in this row and number of elements in this column are equal. And what is the meaning of number of elements in a row? That is the number of columns of the matrix. And what is meaning of number of elements in a column? Number of rows. And that's the reason why when you find the matrix product, the number of columns of the first matrix should be equal to number of rows of the second matrix. Now, when you consider points in the two-dimensional plane or points in the three-dimensional space, you can associate the points to be a 2 by 1 matrix or a 3 by 1 matrix. And that's what I already mentioned. You call vector or it will be the column matrix representing a point, etc. And again, if you have a 2 by 2 matrix, if you have a 2 by 2 matrix multiplied to a 2 by 1 matrix, that is A, B, C, D multiplied to some x, y, you will get one element and in the first row, one element. This will give you x, y mapped to PQ. Or you will say the matrix is actually mapping the point xy to the point PQ. In that sense, every 2 by 2 matrix is mapping a point in the two-dimensional plane to a point in the two-dimensional plane. And if you write xy plus some other element, you know matrix properties of matrix multiplication, the associative linearity, many properties we have. And using that, you get this particular function is having many beautiful properties. You call these properties that represent the function is a linear function. You call the function is a linear function. Linear means something else, and say I'll discuss it later. Many beautiful properties. And so, a matrix is always mapping points in the two-dimensional plane to points in the two-dimensional plane if it is a 2 by 2 matrix. And if it's a 3 by 3 matrix, it will be again what? Mapping from R3 to R3. So, linear transmissions will be, or transmissions will be from a set to set. You call what properties the set is having. So let us look at the set of all points on a plane, or equivalently set of all column matrices of order 2 by 1. Or similarly, you consider two-dimensional plane, three-dimensional space, you consider primarily. So three-dimensional real space. So the name three-dimensional requires something more. Some explanation is needed. I'll come to it later. So 3 by 3 is sorry. In the case of three-dimensional space, you have points represented by 3 by 1 matrix. And now let us see what properties the matrix multiplication have. We will do that with certain examples. We will do that with certain examples. I could have avoided this if I had prepared the slides meant for this only. Please excuse me for this. Okay, let us check. Consider a 2 by 2 matrix. A 0 1 1 0. So the matrix A is 0 1 1 0. What is the effect of this matrix? That's what we explore. You know, any column matrix xy represents the point xy on the real plane. And this point you can imagine to be, this point you can imagine to be the vector sum of these two. So you have the vectors I and j, the unit vectors I and j on the real plane, unit I along the positive x-axis, unit vector j along the positive y-axis. So if you want to get the point xy, or if you want to get this vector, if this point is P, if origin is O, how will you write the vector OP? OP will be, this length will be how much? This length will be X. So this vector will be Xi. And the other length that will be Y. So the corresponding vector will be YJ. And using the vector addition rule, vector OP will be Xi plus YJ. So in that sense, any point can be expressed using I and J. But actually, what is I? I is the column matrix 1 0, is it not? And what is J? J is the column matrix 0 1. So any point xy when expressed as a column matrix, if you write that point in the language of vectors as xi plus yj, in the language of column matrix, the same point xy can be written as x times the column matrix representing I plus y times the column matrix representing j. Is it not? So, if These two, 1, 0 and 0, 1 are reserved as two special points on the real plane, two special objects on the real plane. Any point on the real plane can be written in this format. Okay, you say 1, 0 and 0, 1 have some specialities. The same type of specialities I and J are having to represent points in terms of position vectors. Okay, so that I want. So if I take the matrix A equal to 0, 1, 1, 0, I first try to find out what is the effect of the matrix when multiplied to the special matrices or special column matrices 1, 0 and 0, 1. So A multiplied to A into 1, 0. That will give you what? 0, 1, 1, 0 into 1, 0, and that will be equal to 0, 1. Is it not? 0 into 1, 1 into 0, that is 0. 1 into 1 plus 0 into 0, that is 1. So that means this matrix is converting 1, 0 to 0, 1. Similarly, what is A on 0, 1? For that, you need a similar calculation. The matrix is multiplied to what? Matrix is multiplied to 0, 1, and you will get that to be 1, 0. Okay, so I am doing that. What is matrix A multiplied to 0 origin? It is origin only. Matrix A multiplied to 1, 0, the special matrices, column matrices 1, 0 and 0, 1 are given in different color. So A 1, 0, that will be 0, 1, 1, 0, that is 0, 1, and this is it. So what you get is A multiplied to xy, and that is 0, 1, 1, 0 multiplied to xy, and that is equal to yx. So 1, 0 is converted to 0, 1. 0, 1 is converted to 1, 0. Xy is converted to xy. Origin is converted to origin itself. 1, 1 is converted to 1, 1 itself. Is it not? 1, 1 is converted to 1, 1 itself. So the matrix is capable of making changes in this fashion. The matrix A is capable of changing in this fashion. Points can change in this fashion. So when you look at this, geometrically, the point xy is the point xy is mapped to the point yx. Origin is mapped to origin itself. 1, 1 is mapped to 1, 1 itself. AA is mapped to AA itself. That means the entire line y equal to x is mapped to itself. 1, 0 is mapped to 0, 1 means positive x-axis is mapped to positive y-axis. Positive y-axis is mapped to positive x-axis. Or you can say x-axis is mapped to y-axis. Y-axis is mapped to x-axis. And xy is mapped to yx. So you are getting a mirror reflection about the line y equal to x, and the geometrical effect of this matrix, geometrical effect of this matrix 0, 1, 1, 0 is what you are taking. You are getting the reflection about the line y equal to x. You are getting the reflection about the line y equal to x. Similarly, can you write the reflection about the y-axis? So if you want to get reflection about the y-axis, a point xy should be mapped to somewhere in this, because I've taken the point on the first quadrant, its image will be in the second quadrant. So xy will be mapped to some point in the second quadrant. How much is the distance from the y-axis to this point? The same distance you will move to the left. Okay. And the y coordinate is not changing because you are finding the point and same height. But the x coordinate changes. Negative. So you will get the point minus xy. Okay. So this change, this transformation a corresponding matrix. Let us see what that matrix is. If you consider the matrix minus 1, 0, 0, 1, you will get xy mapped to minus xy. So you get this will say a reflection about the so the matrix minus 1, 0, 0, 1 causes a reflection about the y-axis. Now, can you imagine what will be the matrix representing reflection about the x-axis? So for that, the point xy should be mapped to x minus y. Is it not? Point xy will be mapped to x minus y. So try to find out the corresponding matrix. Try to find out the corresponding matrix. This is reflection about the y-axis. The matrix is minus 1, 0, 0, 1. And if you consider 1, 0, 0 minus 1, you will get 1, 0, 0 minus 1 will map xy to x minus y. And that will be the reflection about the x-axis. Now, rotation through 90 anti-clockwise. I'll come to it in a different way. Suppose you have the xy plane. Imagine this triangle. This point is xy. See, if you make a rotation through 90-degree anti-clockwise, imagine this is leaf of one pole. It turns through 90-degree. You will come to such a position. The leaf will come to such a position, turning through 90-degree anti-clockwise. But when this triangle through 90-degree anti-clockwise, the length of so this length x is now here. This will be here. So these are of lengths x and y itself. But what will be x coordinate of this point? The distance from the y-axis, that is y. But because you are moving to the left side, that will be minus 5. Is it not? And at what height you find the point, the y coordinate will be x. So xy is changing to minus 5x. So if the point vector xy is changing to minus 5x, what matrix you have here, that will be the matrix making a 90-degree rotation anti-clockwise. Okay, a matrix will be capable of a rotation through 90-degree anti-clockwise, and that matrix should have what equation? A x phi equal to minus by x. A should be a 2 by 2 matrix. Let us see what the matrix is. So this is what you get. You get one parallelogram being converted to another parallelogram the edges are rotated through 90-degree. Edges are rotated through 90-degree. Okay, anti-clockwise. You will get another parallelogram of the same type. Now, now rotation through 90-degree anti-clockwise is done using the matrix. You should check it 0, -1, 1, 0. Now you can check that this matrix will make a rotation through 90-degree clockwise. So I will give you the general situation. Suppose you want to make a rotation through an angle phi anti-clockwise, the matrix will be cos phi minus sin phi, cos phi. So just imagine phi equal to 90-degree. Just imagine phi equal to 90-degree. So cos 90-degree minus sin 90-degree, sin 90-degree, cos 90-degree. That will be your matrix. 0, 1, -1, 0. Sorry, 0, -1, 1, 0. And this is transforming the point x by 2, x cos phi minus y sin phi, x sin phi plus y cos phi. So this is a matrix making a rotation through an angle phi anti-clockwise. And these are some of the geometrical effects made by matrices. So given the another pictorial representation of that rotation through an angle 90-degree anti-clockwise. Okay. So I'll ask you if the matrix is making an angle rotation through 90, sorry, through an angle phi anti-clockwise, what would be a square, a cube, etc. A square means A acting twice. So you see, if A is acted once, it makes a rotation through an angle phi. If A acts two times, it makes a rotation through an angle phi two times. So effectively, you have made a rotation of two phi. Similarly, A cube will be making the matrix cos 3 phi minus sin 3 phi, sin 3 phi, cos 3 phi, etc. Okay. Now, now consider this matrix. This is an interesting case. The matrix 1, 3, 0, 1. That is, again, I'll come to what is a linear transmission, etc. later after this geometrical expressions. Um, if you consider the square, unit square on in the first quadrant, so this will be transformed to a suitable parallelogram again in the first quadrant. So imagine you have pasted your photograph here. Your photograph is fixed here. And then you are applying the matrix on the plane. Along with this transformation, your photograph also gets transformed. So your photograph becomes a deformed, the shape will be changed. So it's your photograph, it will be deformed. The shape is changed. Okay, so I'll let you imagine that what happens to this shape. This was the place I asked you to fix your photograph. And after applying this matrix 1, 3, 0, 1, the photograph I told got deformed. So you get the deformed shape. You call it a shearing. This is called a shearing. Shear. And you say That matrix is a shearing matrix. The matrix is a shearing matrix. And towards which side it is shearing? Towards the right side. So it's a right shear. You call it, it's a right shear. Right shear. Now, let us see what type of matrix it is. It's an upper triangular matrix. What is upper triangular matrix? Below the main diagonal, all entries are zero. Only one entry is here, that is zero. So that's upper triangular matrix. So upper triangular matrix will make shearing. And what is determinant of this matrix? It is 1, positive. So a matrix which is upper triangular and having positive determinant, that will make a right shear. So you would have got which type of matrices can make a left shearing? Which type of matrices can make a left shearing? Upper triangular matrices with a negative determinant. Upper triangular matrices with negative determinant can make left shearing. So the role of determinants also is there to study geometry. When you look into the geometrical aspects, determinants also have this right shearing matrix has got the properties one upper triangular and then positive determinant. If you have an upper triangular matrix with negative determinant, it can make that. Okay. Now, shearing can be towards right or left. That's what I said. Shearing can be towards upper side or lower side. For that, you can guess which type of matrices will be there. Lower triangular matrices will be passing vertical shearing. Horizontal shearing is passed by upper triangular matrices. Vertical shearing is passed by lower triangular matrices. That is also, if the determinant is positive, the shearing will be towards one side. Determinant is negative, the shearing will be towards the other side. So determinants are having some role in. Now we say matrices are capable of making changes on points in the two-dimensional plane or three-dimensional space. Now, let us look at the properties of points in the two-dimensional plane and three-dimensional space. So let us see two matrices x1, y1 and x2, y2. These are two matrices or 2 points in the two-dimensional plane. You know, their sum equal to x1 plus x2, y1 plus y2. That is another point in the two-dimensional. And earlier I told x1, y1 can be written in the vectors as x1i plus y1j. And this is x2i plus y2j. And this will be x1 plus x2i plus y1 plus y2j. Is it not? This is x1i plus y1j, and this is x2i plus y2j, and you are asked to find the sum of these two, and you get the right side. Right side is what? x1 plus x2i plus y1 plus y2j. Is it not? So you are getting the sum of matrices written in the language of vectors. Okay. And that will actually give you the point x1, x1, y1 and the point x2, y2, the point x1, y1 and point x2, y2 can be added in a meaningful way to get the point x1 plus x2, y1 plus y2, x1 plus x2, y1 plus y2. That means points in the two-dimensional planes can be defined on the two-dimensional plane. A similar idea can be had in the case of points in the three-dimensional space also. For that, you need to consider the vectors ijk. Coordinate-wise addition is the meaning of addition of points. So if you take R2, if you take R2, the two-dimensional plane, or if you take R3, the three-dimensional space, they will contain points, and the points can be added. And what's the process of addition? Coordinate-wise addition. Now, because I am restricting our discussion to the two-dimensional and three-dimensional planes spaces only, you can imagine in the next higher levels. In the next even Rn also. Okay. So in Rn also you have the coordinate wise addition. Now, if x1 y1 is a point, you know it can be written using vectors, etc. In the case of vectors, you have scalar multiplication. In the case of vectors, you have scalar multiplication. So product of a scalar with a vector. So that you can have here also. So what do you mean by 2 times x1 y1? That is 2x1 plus 2y1, is it not? That is 2x1, 2y1. So here, what you have done, the multiplication you have done on each of the. Now, the two process we have done, the two process we have done on points, set of points in R2 or R3, they are addition and scalar multiplication. So addition and scalar multiplication are two operations defined. So for that you need x here when you do it on the plane R2, when you do it on the plane R2, x equal to R2, and when you take the scalar, scalar will be from R. Scalar will be from R. So x is a set. Many points are there. So you would say x is a non-empty set. X is a non-empty set with many points, and R is the set of real numbers. And the set of real numbers is a field. Field you will study in classes in algebra. So field means there are two operations, addition and multiplication. Two operations, addition and multiplication. With respect to addition, you have the commutative property, that is y plus x, associative property, x plus y plus z equal to x plus y plus z, existence of additive identity, existence of additive inverse for every x minus x inverse, and commutative property, x plus y equal to y plus x. So binary operation which is closed with and have the properties in associative, existence of identity, existence of inverse to every element, and then commutative property. And with respect to multiplication, also the same thing happens. Then you will say A set with these two algebraic structures to be a field, the simplest field you can think of will be the simplest field you can think of will be, excuse me 1 minute. Okay, let us continue. The simplest field with we have is the set of real numbers. Set of rational numbers also is a field. Set of complex numbers is a field. That will study in algebra. Anyway, you have X to be a vector space. Here it is R2 and R is a field. So you say F equal to R. F equal to R. Now, the addition you process on addition you perform on X, that is R, and scalar multiplication you do with one element from F and one element. These two will have, that means when X is a non-empty set and F is a, if you have addition, this is a binary operation on the set of non-empty set X and a scalar multiplication. For that, you take one element from F and one element from X, and these two operations will have certain properties. And what are the properties that we will check? X is a non-empty set. F is a field. F is a field. There is vector addition. Vector addition. So I'll say vector addition because later I'll call X to be a vector space. So points in X are known to be vectors. So addition of points in X is vector addition and scalar multiplication. Scalar multiplication. And the vector addition and scalar multiplication satisfy some properties. With respect to vector addition, X plus is an abelian group. That means 2 points can be added in any way or any order if it is same output. Associative properties, identity, identity. In R2, there is no the point 0, 0, 0, 0, 0 vector, point vector 0, 0, will be the identity. And for any pair x bar, minus x minus y will be the active inverse. So these are having in this R2. Now, scalar multiplication means in the case of points in R2, scalar multiplication is actually making a scaling, either magnification or compression of the size. So, scalar multiplication. So, with respect to scalar multiplication, some distributive properties are there. So, if alpha is an element of F, alpha element of F, x, y element of x, then alpha multiplied to the sum equal to alpha x plus alpha y. If x and y are in x or x is in x, alpha beta element of f, x element of x, then alpha plus beta times x equal to alpha x plus beta x. So one condition is that x together with the addition should be an abelian group, and the other condition is for every alpha element of f, xy element of x, alpha times x plus y equal to alpha x plus alpha y, and the third condition is alpha beta element of f and x element of x implies alpha plus beta x alpha x plus beta x. If these conditions are satisfied, you say X is a vector space. If these conditions are satisfied, we say X is a vector space over the field